Alright, 6-4, and we're only spending 1 day here. You are going to be proving those log properties for the natural log function. Let's do those log properties we had before were, there's just the 3 of them. The first one, log base b of a product expanded to the log base b of the sum. The second property, log base b of c divided by d, went to the difference of the 2 logs, log base b of c minus log base b of d. And the third one, the power rule, the exponent one, where the exponent comes down as a multiplier, log base b of c to the r power. The property says the exponent can come down as a multiplier, so it's r times the log base b of c. So and I told you these were true for natural logs, and we've been using them. In this section, the author wants you to be able to prove that those properties are true. In that, we are going to be using the exponent property, so I want to quickly review your exponent properties from Algebra 1. Exponent properties. 3 rules here. If you've got a base to a power multiplied by the same base to a different power, remember like x squared times x to the 5th, you add exponents here. So you would add the c and the d. If I've got a base to a power divided by a base to a power, rule is you subtract these exponents. Numerator minus denominator. And then the third one, b, c to the d, a power raised to a power. That's when you multiply your exponents. Okay, these exponent rules are going to be used in the proofs that we're going to do today. So we are doing 3 proofs. We're going to prove each one of these properties for the natural log function. And what we're going to use to prove them is called the uniqueness theorem. You may have to give this back to me at some point. Hint, hint. The uniqueness theorem says, and it's very easy, it's 2 parts. If 2 functions have the same derivative, so they have the same derivative and they have a point in common, then they are the same function. So, 2 things you have to do. Show that they have the same derivative and show that they have a point in common. Then you can say they are the same function. So, by uniqueness theorem, we're going to prove these 3 properties for the natural log function. Alright. So, our first proof. We are going to prove that the natural log of a times b equals the natural log of a plus the natural log of b. Got that a little close there. Alright. So we're going to do 2 things. We're going to let function f equal the left-hand side of this equation. And we're going to let function g equal the right-hand side. Now, if I can show that these 2 functions have the same derivative and they share a point, then I know these two functions are the same function, which would make them equal each other. So, our first step on these proofs is to identify each side of the equation as a separate function. Now what we're going to do is let b be a constant. It's a number. Treat b as a number. B is a constant, and we're going to let a equal a variable x. So b will be treated as a number, a is going to be treated as the variable x. So now we're going to rewrite. So function f would be the natural log of b is the number, a is an x. We usually write the number first. So that gets rewritten bx. Because a got replaced with an x, b is a constant. We usually write like the 2x or the 3x or the 4x in front, the numbers in front. Over here, same thing. G of x would now equal a is the x, so natural log of x, and b is a constant, natural log of b. Alright, so uniqueness theorem says the first thing I've got to do with my two functions is show that they have the same derivative. So I'm going to do the derivative of f. So I'll just say what I'm doing over here. Same deriv. Okay, it's a natural log. The rule there is 1 over the u times by the derivative of this. Remember, b is a number. Think of it as a 2. The derivative of 2x would be just the 2. So it's just the constant b here. That's my derivative. B's would cancel. 1 over x. Over here, derivative. Derivative of the natural log of x is 1 over x. Derivative of x is 1. This is a constant. This is like a 2. Derivative of any natural log of 2 is a number. I don't even know, 1 point something. But that goes to 0. So my derivative, 1 over x. So they have the same derivative. Okay, I'm halfway there. Now I've got to show that these two original functions share a point. And this is where the trick comes in. The trick is not the same on all three of these. For this one, so we want to show that they share a point. So we go back to it's the original functions that have to share a point, not the derivatives. So if we go back here, if I let x equal 1, and find f of 1, which is right here. Here's my function f I'm using. Natural log of b times 1 is natural log of b. So the point that I have found has an x value of 1 and a y value of natural log of b. Over here, g of 1, natural log of 1 plus natural log of b. And if you remember, maybe you don't, the natural log of 1 is 0 plus natural log of b. So I got natural log of b again for my y value. So when I put 1 in for the x, we simplified down to natural log of b. So now I've shown that they share a point. Specifically, they share the point 1 natural log of b. So by uniqueness theorem, the natural log of a times b is the same function as the natural log of a plus the natural log of b. Okay, 1 down, 2 to go. Alright, the second property that we're going to prove is that the natural log of a divided by b is equal to the natural log of a minus the natural log of b. So again, first thing we do is we separate this into two separate functions. So I will let f of x equal the natural log of a over b. and I'll let g of x equal the natural log of a minus the natural log of b. Technically, I shouldn't be calling these functions in terms of x because I haven't introduced the x yet. I kind of do that second, but that's okay. So now we do the same thing as before. We let b be a constant. So treat it as a number. Pretend it's a 2 as you're doing the problem, but don't write it as a 2. And we will let a equal our variable x. So then we'll have functions in terms of x. So technically I should be doing this first and then breaking those apart. So my real function f of x, a is the x, so I've got x, natural log. A is the x, b is the constant. And then g of x equals natural log of x minus natural log of b. Where am I here? Oh, down here. Okay, here we go. First thing on uniqueness theorem, show that they have the same derivative. So show same derivative. Okay, so f prime of x. Okay, natural log of a u. So it's 1 over this. So it's 1 over this fraction times by the derivative of this. Think of this, x over b, if I need to, I don't know, maybe right here. X over b as 1 over b times x. Like think of the b as a number, like 1/2 x. So the derivative here is this 1 over b. Okay, let's, so I've got fractions within fractions here. Let me take care of that first. I'll make this 1 over 1, so I'm just going to pretend that this isn't even here. I'm going to flip this bottom one over, multiply it by the 1 over 1 that I have here. So that becomes b over x. Same thing, this is just 1 over b, because it's divided by 1. My b's cancel each other out, and I'm left with 1 over x as my derivative. Over on this side, derivative of natural log of x is 1 over x. Derivative of a constant, remember b is like a 2, natural log of 2, there's even an x there, that goes to 0. Okay, they have the same derivative. We're halfway there. Now we have to show that they share a point. Show that they share a point. On the first one, we let x equal 1. Here, the trick to showing that they have the same point is to let x equal b. How do you know this? Mathematicians know where it's going, they can see it. You've just got to memorize it. So we want to do f of b. So go back to the original f of x and substitute in for x, you're going to put in a b. So it becomes the natural log of b over b. b divided by b is a 1. The natural log of 1 is 0. So the point we just identified on f of x was when x is a b, the y value comes out 0. If we do the same thing over here and find g of b, the same thing should happen. So go to function g. In place of the x, we're going to put in a b. So natural log of b minus natural log of b. So no matter what b is, I'm subtracting it from itself. Anything subtracted from itself is 0. So again, we got b 0. Same point.